let me introduce the Rodrigo Carrasco. Is our Associate Astronomer at Gemini South, and he's gonna talk about the GMOS mask making process. Please go ahead.
Okay, can you hear me well?
Yes.
Okay, thank you very much. Thank you very much for assisting this workshop of mask making. I am talking also on behalf of the Gemini staff because it's many people are involved in the mask making and installation of the mask and design and cutting with the laser machine. Okay. I will start with my talk to refreshing a little bit about the tools and definitions. To make a mask, we use the Gemini mask making preparation software, shortly call it gmmps, which is the current version of this software is the version 1.5.2, and it's work with the SkyCat version 3.1.4, and the software is capable to make mask for Flamingos-2 and GMOS South, North, and regarding the F2 MOS mask, I think Ricardo Salinas will talk about these new capabilities with Flamingos-2 and the infrared. A very good documentation you can find in this the URL given in this presentation. Written by Misha Schremer. It's a very nice documentation, and you can find a lot of examples there. About the definition, it's important to understand the different anachronisms we use at Gemini. One of them is the object table, which is the table in fit format containing the information for the mask design for the gmmps. There are also some software that you can use to prepare your object tables. Such as Circ Extractor or Gemini IRAF and PyRAF task that we have in the Gemini package. And another definition that is important is the ODF or object definition file, which is the mask. When you design the mask and you finish your mask design, this is the mask that you submit to Gemini via the observing tool. And finally, you have the MDF or mask definition file, which is the processed file by the Gemini staff that is used by the user to reduce the MOS observation. In order to show you how this gmmps works, I will start to work with, I will show you an interactive example of how to design a mask, especially. The mask can be created, of the object table, in order to create a mask, can be you can use two type you can use two approaches. One is using pre-images, where you can observe with the same instrument, and another is using external catalogs and images, which we call pseudo images. There are some advantage and disadvantage of using the different approaches. Using pre-images have the advantage that you will have an accurate relative position of the slits. And basically, the image will be available immediately after they are observed and processed by the Gemini staff. And also, you minimize any effect of the proper motion over the target that you want to observe, particularly if you are looking for point sources. The disadvantage is that you require additional time, telescope time, of course, and you have to wait until the pre-image is observed and in order to design the mask. And also, this is problematic, especially for programs that have targets in the semester boundaries. Using external catalog is an images is a very good option because you don't have to wait until the Gemini observe the pre-imaging, and you can design early your mask. However, the disadvantage, well, I don't think that is a disadvantage, but you have to be very careful about the catalog that you're using, and you need a very good accuracy in the target coordinate, and also you have to watch very carefully the proper motion effect over your target, in this case for point sources. I will present some example on how to design a GMOS mask. I decided to use an old image. We use it to to construct a mask for band shuffling. And it's using a GMOS South pre-imaging, which was observed with the old A2B CCDs. And these pre-images must be treated as an external image because for three important effects. One, the different pixel scale we have between the old A2B CCDs and the new Hamamatsu CCDs are different. Also, the gap size between the CCDs are different, and the distortion solution that you have to pass to the laser cutter machine also is different. Therefore, you cannot use just only the pre-image observed with the old A2B CCDs to construct to design your mask. You have to do some work on this, and you have to treat this image as a pseudo image, and you have to construct the object table based on target. To do that, you can use some of the tool we have in the GMOS package, which is the task GMS create, and this can be used to create the object table and the pseudo image. An example of this is the image in the right is the original pre-image taken with the A2B CCDs, where you can see that the map of the field of where the mask is covering is completely different for the Hamamatsu CCD. The gmmps software support only the Hamamatsu CCD, not the A2B CCDs. And we can see that the two of the stars that originally were selected to align the mask on the sky are not usable. One is over the gap, another is very close to the border of the area that covered the slit. So basically, original pre-image cannot be used. Then, in order to work and to create an object table, as I say, we have to use this GMS Mask Creator. Here is an example of how it's working. Then you create a new object table, and you create a new pseudo image to map to resample your old image taken with the old CCD to the new Hamamatsu CCD. And in the right, you see the transformation between the two systems. Sorry, the two systems, and you can see, for example, for the X and Y scale, you have a magnification, of course, because you are mapping from the smaller pixel scale to large pixel scale. Also, you have some rotation effect that you have to correct in this case. And then I am going right now to the interactive session to show you how this works. Let me open here the gmmps. I already opened it. Then I will open the fake image that I was producing using the GMS create, and I can adjust the cut level here to the level I want to show in the image to see the target. This this mask is the idea of this mask is to try to observe some gravitational arc around this central VCG galaxy. Then this is why we are using band shuffling in order to minimize the effect of the skylines in the subtraction of the spectra and try to find the correct redshift of the galaxies. In order to work with the object table, first I load the object table file from the gmmps menu, where automatically show me the area covered by the mask. The rectangle in the right size is used for the barcode that we use to identify the mask in GMOS. Then it's important to basically show where it's located in order to minimize and to not put a slit or acquisition stars in this region. Acquisition stars are these rhombi. I don't know if red or magenta color indicated in the mask. Well, you can see that there are some alignment stars that is selected, which one is in the gaps and another is in very close to the border. then if I leave these two alignment stars in, the software will not be allow me to construct the mask, basically to design the mask. Basically, because we are interested to build or design another and shuffle mask, I have to use this configuration for the and shuffle mask. I will show you that basically I get an error saying that one of the acquisition stars is too close to the boundary. If I can remove this star by basically clicking over the desired star here and ignore it. When I ignore it, basically the software allow me to design the mask. However, we have another problem here, which is this star. This star, then we have to also remove it because it's over the gap and we are not allowed to have stars, alignment star over the gap. And I do this, I use the same procedure. Basically, I click over the stars and ignore it. Now, I have the possibility to design the mask with the configuring nodal and shuffle, and then I will have this small window where I can select or band shuffling or micro shuffling. I am using band shuffling because my objects are packaged in the central region of the CCD of the GMOS field of view, and I am interested only in the 1/3 of central region in order to design the mask. And in this case, I leave the default shuffle ambient pixel and arc-second because all the slit will be located in the region that is not shadowed. The region that are in yellow at the top and at the bottom cannot have any slit there, because otherwise if you have a slit, the mask is not corrected design. Then I can now design the mask. In this particular target, I am interested to use the R400 grating. You can use any grating that you want. And also a blocking filter. I am adding here another blocking filter in order to eliminate everything below 550, 15 nanometer, and avoid any second order contamination at the very red end. And the central wavelength at 750. Here, by default, the system uses the blaze wavelength for the grating R400. And you can basically increase the separation between a slit to, by default is 4, but you can reduce to 3, but 3 or 4 is okay. And you can pack the spectra, but for the nodal and shuffle doesn't make any, there is no differences. The only thing that you cannot do is auto expand the slit, because for band shuffling, the slit length are fixed. In this case, we are using a slit length of 2 arc-second. Okay, I will explain why, because we take the sky in another position. And then you can basically design the mask. And here you have some kind of warning saying that the second order overlap will be above 1 micron, which is okay for the case of this mask. Another message saying here is that there is no information of the proper motion entries in the PPMXL catalog, which is used by default by the gmmps. However, I will show you how that you can check. You can check in another way if your alignment stars have high proper motion or not, which is very important, by the way. Well, here is the first mask you have designed. Of the 88 available objects, you put 28 in the area, which contain 4 alignment stars, which is priority 0, and then the priority of the objects are from 1 to 3, where 1 is the highest priority, the red circle here. 2 are the cyan square, and 2 are the green triangle, and priority 3 are the green square. Then at total you have 16 objects, including 4 alignment stars. However, I need to check the mask before I go further, because I suspect that one of the alignment stars, which is here, this located here, will interfere with or will eliminate one of the target that I am interested in the central region. Then how to check this object definition file created by gmmps is simple. You open the ODF file. It's displaying a completely different window with the blue color here, and then you can check the slit spectra over the image, and you can see basically that all your slits are located inside the allowed region for the band shuffling, and there is no target outside this central region of the target. However, as I suspected, this star here, which you can check, this is the highlight acquisition star, just only clicking by highlight acquisition star here. As I suspected, this star basically is passing, the spectrum is passing over the central region where I am interested to put more objects. Then I can eliminate that star by editing. I can close this file, and I edit that star and ignore it. And also, I will ignore this star because it's outside the field, which doesn't matter because it's outside the field. And then I can try to design a new mask to see if I can put more objects there. Then I override the same. Then I can check if the ODF is good. Yes, okay. I can see that I have now 3 alignment stars, this central star here, and 2 here at the forming a triangle, which is not perfect because normally a good mask design should be, the star should be distributed very well across the entire field of view. For example, if this star will be low, will be better, but it's not bad, and you can have a good alignment on the sky. Then when you're happy with this, you can check the slit spectra to see if everything is okay. By the way, there is many ways to edit the object table here. In particular, you can edit, subtract, eliminate target. However, if you are doing that, will be saved only in the cut format of the SkyCut and not in the fit format. Then if you close the gmmps and open it again, you will lose that information. It's important to remember that. When you are happy with the mask, then you can submit the mask to Gemini. I will come back to my presentation. And then one of the important things that you have to remember is that when you create a new mask, and you open the ODF, you will have all the information regarding the position, the target, the central position of the mask, and the grating using, and the central waving, and that information should be go to the observing tool. It is important that when you observe, when you design a mask from external catalogs and images, you have to be carefully look at the position angle that you want to use, and in order to use a bright enough guide star, this is the first thing that you have to check with the observing tool, and then put the coordinate and the correct parameters that the ODF, the object definition file, is given to you. Here in example, I opened the mask design, the ODF, and then I added the correct coordinate to the. You have to put the correct coordinate to the in the target component in the observing tool. Another important thing is that you have to put the correct position angle. In this case, it's easy because the GMOS South pre-imaging taken with the old CCD will use the same guide star, and there is no problem. But for other images from other catalogs or telescope, then you have to search for a good position angle for the good distribution of your target, depending on your science, of course. And then you have to add the information about the central wavelength and the filters and dispersers that you are using. And you can see that here it still appears to be changed to Hamamatsu, and of course the mask number that you want to observe in this sign. Another important thing with nodal and shuffle is that you have to update the nodal and shuffle section in the observing tool in order to put the correct parameters of the offset detector rows and offset arc second. Okay, this parameter very important because it's used for the shuffling and the offset. And in the case of band shuffling, because the central region is too crowded, we are offsetting to only one direction. We are not offsetting around the target. And then here we are offsetting 120 arc second above the central part of the cluster in this case. For the micro shuffling, normally you have to offset around each target. Then some key points and summary. I'm summarizing here because I want to give the possibility to Ricardo to explain in more detail about Flamingos-2. Then regarding acquisition start, the acquisition start must be not saturated, and this is very, very important. At least between 2 and 4 acquisition start, recommended are 3, should be selected to design the mask from the images of pseudo images. No? More than 4 acquisition stars are completely unnecessary. Then don't put 6, 7, 8, or 9 acquisition stars because that will increase the overhead of the observation when we center the mask. Also, acquisition stars should be well distributed if it's possible. Sometimes it's not possible, the geometry, but you have to try to find the best geometry for your acquisition star because that will give to you a very good solution of the centroid and of each star, and they put the mask in the correct place. And should be bright enough, but not saturated, and bright enough in the sense that you can see it in 10-30 second exposure. Normally, start with magnitude 16 to 19 is good enough in 10-15 second exposure to acquire the mask and align it. And of course, similar magnitude. I mean, you cannot put a 14 magnitude star with 90 magnitude star because we will have difficult to align correctly the mask. The galaxies to use as an alignment star are not allowed because it's very difficult to calculate correctly the centroid. And try to select the star should be selected away from the border for any gaps. Another important points are check the slit. Check that the target are inside the slit, of course. Pay this attention because if you see that target are not inside the slit, or you see that target are in one of the slit is outside left and another is outside right, there is something wrong with the target coordinate of your catalog in the case of external catalog. Also check the slit width. Normally the slit width selection should be follow the same slit width we have for long slits. If you are using non-standard width, then you have to be aware that the calibration means the flux standard, another radial velocity star, etc. Will be observed as closer to the matching slit width that you selected for your mask. Again, slit near the edge of slit outside the area of the area of the mask will not be cut by the laser cutter machine. This is unavoidable, and also slit outside the cyan slit placement area that I show in the previous slide. Finally, then some nodal and shuffle recommendation. You have to be sure that the slit length and key offset in the observing tool must be consistent with both node positions. This is important, as I show also the nodal and shuffle offset and the offset in the detector rows must be identical. Nodal and shuffle mask using tilted slit is important. You can use it to the slit, but you cannot not in the Q direction, and it's very critical at this point. The slit must not be appearing in the storage band in the yellow region, and basically, and the last A slit in the microshuffle mask, which is not shown here, must have the same length. Some storage area between the signs also bands at least should be as high as the band that you're using to design your northern shuffle. And some recommendations for the observing tool that I already showed, which is very important. I think that if you have any question, we can talk it in the chat session, which is Tuesday and Wednesday between 11:30 and 12 p.m. Hawaiian time. Thanks for your attention.
Thanks, Rodrigo. Let's move on to the second part of the workshop. So Ricardo Salinas is our assistant scientist, and he's gonna give you the instruction how to make the Flamingos-2 mask. While you are preparing, I want to remind everyone, you guys can still post the questions for Rodrigo while Ricardo is giving his presentation.
All right, can you see this?
Yes.
Thank you. Okay, thanks for staying until the very end of this session of today. So this is going to be just a continuation of Rodrigo's talk. And while he was talking about GMOS, I'm going to be talking about Flamingos-2. Flamingos-2 is the imager and near-infrared imager and a spectrograph at Gemini South. And its multi-object spectroscopy capabilities have been recently commissioned. The commissioning is about to be finished, and we're very soon is going to be offered for you to take spectra with this, lots of spectra with Flamingos. So, this is, I would like to start saying that I have good news. The good news is that if you already know how to design a GMOS mask, or if you were paying attention to Rodrigo's talk, then you already know 90% of what you need to know. There's nothing to be afraid. Flamingos masks are almost identical to GMOS masks. We're going to be talking about the same software, gmmps, and all kinds of things that you heard already, acquisition stars, guide stars, catalogs, and all that. All is very similar. The one thing that is a bit different is how you actually execute the observations. These are different in the near infrared compared to the optical, and that may change a little bit how you design the masks. So let's go into just some kind of refresh, some reminder of what is different between the near infrared and the optical. So what is different is the sky. The sky is essentially different. If you see this table I put here, it shows you different surface brightness for the sky. If you go to some observatories, some dark side, you're gonna have this progression, let's call it, of surface brightness. When you are in the blue, surface brightness is very low in terms of magnitudes, but as you move into the red, into the near infrared and beyond, into the mid infrared, things go higher and higher. The sky gets brighter and brighter. So this changes things, and you need to do things in a different way. So why does this happen? And the difference is this emission in the sky, this OH emission lines that you have on the near infrared sky. If you have ever, for example, done some, I don't know, calcium triplet spectroscopy, this is around here, right? And you have some emission lines, OH lines, but these are actually very small compared to what you have in J, especially in the H band and also in the K band. So if you have troubles measuring your calcium triplet, you're gonna have huge troubles here. So you have to do some things have to be different. And then the emission is not only intense, but also is varying in time. So what this movie is showing you is some kind of experiment that was done early on with 2MASS. And this is showing you just a patch of the sky, some kind of 9 degrees on the sky. Let me put it again. And it's showing you the variation of the sky in the H band. So these are not clouds. This is actually the sky brightness varying in a very fast way. So each frame, or I think each frame is something like 9 minutes. So this is a kind of time-lapse movie, right? So that tells you that in the order of minutes, you have this huge spatial variations and also temporal variations. So that's the main difference between the near infrared and the optical. And the other thing, so I want to, if I can go back a little, I told you about this thermal background that starts appearing, let's say, around 2 microns. And this is basically, well, everything that has everything that has a temperature in the universe has some radiation associated to that temperature. So if you consider something in a room temperature around 300 Kelvin or a bit below that, you have this basically a black body curve that starts emitting around 2 microns. So everything at room temperature is emitting at those wavelengths. So if you're on a telescope, well, your instrument is, shining, your telescope is shining, the air is shining, everything is shining. Everything contributes to this thermal background. So this is why several spectrographs have trouble going to the K-band. The K-band is just around here, and it's even worse when you get into the mid-infrared. So this is something that becomes a problem in the K-band, and you need some instrument and telescope that can handle the temperature control very well if you don't want to be swamped in this thermal background. So this was some kind of introduction, and so there are 2 take-home messages from this introduction. First, that things are so bright, the sky is so bright that if you go for a very long integration, you're going to saturate very soon. Either you're going to saturate your sources, or you're going to be saturating your detector because the sky is too bright. So your integration, your exposure times have to be short. That's the first thing. And the second thing, you have this background that is varying in a very fast way, in a very small scales. So you cannot just stare. Usually what you do in the optical is just stare. You can stay there 20 minutes, 30 minutes, and that's fine. That is not the case in the near infrared. You need to move your telescope. You need to do some dithering to try to model this change in behavior of the background. So this was an introduction. So let's go now to the instrument itself, Flamingos-2. Here you can see flamingos watching the sunset very nicely. And this table, basically this, Ruben already showed you these numbers before. So what can you do with flamingos as a multi-object spectrograph? You're gonna have an area of 6x2 arc-minutes where you can place your slits. And if you make your slits in a certain way, you can put up to 150 of them. I'm going to show you how is that possible. And then depending on the grating that you use, you can have some kind of a, let's call it mid-resolution, to put a name, where you are concentrating depending on the grating, and depending on the filter that you're using, you can concentrate on the J, H, or K, or you can go for a lower resolution and then have a wider wavelength range, some kind of YJH or an HK region. In terms of the slit widths, you have to use something. I'm going to talk a bit more about slit widths later, but you need to use something equal or higher than 0.54, and this is related to basically the on-instrument wavefront sensor. If you go to, this is what Rodrigo was talking about, how well you can position your targets inside your slits. If your slits are narrower, the narrower they are, the more accurate you need to be in position stars inside the slits. And that is a bit challenging for this wavefront sensing, the behavior of the performance of the OI. So you need this width at least or higher. This is just to show you some kind of end result, something how they look. Something that looks immediately different, you're going to see something that is different from GMOS is that the dispersion axis is different, right? In the case of GMOS, the slits are like this, and you have the dispersion like this. In this case, the dispersion is different. And here is just an example of an exposure. Many slits, 90 targets in observing the K long. So this is, when you take just one exposure, it's really difficult to see anything. You see the skyline, sky emissions, and there are some very faint target there, for example. But in individual exposures, as always in the near infrared, it's very difficult to see things. You need to do the full reduction to actually see your spectrum. But this is just to show you how your raw data is going to look. This is just like Rodrigo said, the task, the software they use to design the mask is the same, gmmps. This looks just like a SkyCat if you have used a SkyCat in the past. This is some kind of add-on to SkyCat that you can use from these buttons here. And so something that I'm going to emphasize more than Rodrigo did is the guide stars. I think you may have your beautiful mask. You can have 150 slits. My mask looked beautiful, and then you realize, oh, I cannot guide. No, that's wrong. Your mask, if you cannot guide, then your mask is useless. So the first thing, my first advice is to determine well your guide star. And how you do that, you need to choose your target, obviously, for your science, but you need to choose what is going to be the center of your field and what is going to be the position angle for your mask. And you can adjust both a little bit so you can find guide stars. So let me show you an example of this. This is, for example, some field in the bulge, in the galactic bulge. So I can use this image. This image comes from the observing tool. The observing tool is the software, Gemini software that you use to design your observations. So we have two things. We have gmmps that you use to design the mask, and then to design your observations, you use the OT, the observing tool. So this is just a screenshot from the observing tool. This is this 2x6 area I told you about, where you can place your slits. And this is showing you the center of the field. And this line here is showing you the patrol field of your wavefront sensor. So you need to choose a star inside this area so you can guide. And this is where the wavefront sensor is, and this is just the arm that moves the probe. What else? So in this case, everything that is marked as with the green star can serve as a guide star. So you have plenty to choose. There are no problems. You're in the galactic bulge, or you're in the disk. Usually you don't have problems. There are lots of stars. So somewhere inside this field of view, there is a star cluster. You cannot see it, but you will see it in the next slide. In a couple of more slides, there's a mystery star cluster there. So let me give you another example. Oh, and what happens if I want to rotate the mask? There is no problem. You can have a different position angle, and in this field again, you have, regardless of what kind of position angle you choose, you're always going to have a good guide star because there are many of these green circles here. But that is not always the case. Let's check this other target. This is a galaxy, an elliptical galaxy, NGC 7796. And let's say I want to, observe global clusters around NGC 7796, and I put my mask like this. I can design my mask, and I have all my targets well defined. And then, what happened? Oh, my position angle. I don't have any guide stars. This is useless. You need to first choose what is the position angle that gives me a guide star. So in this case, it's simple. I can rotate the whole thing by 180 degrees. And I'm going to have the same distribution of my mask, basically. But then I have a guide star. So this was easy to choose. This is to solve this problem. But in this field, you can see that many cases, you may have problems finding a guide star. So that's the first thing you need to determine. If you don't have a guide star, then you cannot observe. So now that we know we're going to observe our target, we know where we're going to place the mask, we know the position angle, now we need targets. We need some catalog so we can design the mask. We need an image. Basically, that's what I'm trying to say. We need an image. And for the case of flamingos, you can do the same things that Rodrigo told you for GMOS. You can either have a flamingos image, or you can use some kind of image from a different instrument, a different telescope, and produce a pseudo image. In the case of flamingos, taking images or using flamingos images are strongly suggested, I would say. So either you have already your favorite target observed with flamingos, or as part of your program, you tell us, okay, I'm going to need an image, so please take an image for me so I can design the mask. So I would say this is the way to do it for now. The pseudo image, I think, needs still a bit more testing, especially if you want to go for a 0.54, what's called the 3-pixel slit, this kind of narrow slits. And once you have your image, well, you need to produce a catalog. You need to measure sources in your image. You can do it with anything you want. You can do it with Extractor, for example, DAOphot or IRAF or something in Python or whatever. But then, so basically, I'm going to be describing this case, and I'm not going to be describing this case that Rodrigo talked a bit more about the pseudo images, images that you produce with this GMask create. In this case, we have our own image, we are running something, detecting sources, and then we need to, this catalog, we need to translate it so GMMPs can understand it. If you have used a SkyCat before, you know SkyCat likes catalogs in a very precise format. So there is a tool in IRF that helps you to go from, let's say, a extractor catalog into something that GMMPs will understand, that the SkyCat will understand. So let's say we took our pre-image of our field. This is the field of the mystery star cluster. This is a very a pre-image is something very simple. It's just four exposures, so 5 seconds in the KS band, and this is with a tether of 15 seconds. This image, or these 4 images were reduced with dragons. And if you don't know what dragons is, I invite you to go on Thursday to Kathleen Labree's workshop on dragons, and then you're going to learn how to reduce things like this. So this image is reduced. It's a flamingos image, and we're ready to design a mask over this image. And in case you're curious, mystery star cluster is there. I made a mistake. I pointed the telescope slightly in the wrong position. So this is why I'm here, to show you and to teach you how not to make mistakes. So don't do this. Try to put your targets closer to the center, I think. Anyway, so we're going to design a mask based on this image and try to observe stars in this star cluster. How do we do that? So I'm going to run Sextractor over my image. My image has many sources, so Sextractor is going to give me many hits, many targets, and you can run it very simply. You don't, well, with Sextractor, obviously you can do many things. You can do things on morphology and different kinds of magnitudes and fluxes, etc. What we really need is something positions and some magnitude. That's the only thing we're going to ask Sextractor to give us. And to give us also as a fit table. Also with Sextractor, you can produce several outputs, and we're going to use just a fit table because that's easier to go to IRF and then to GMMPs. So in this case, I run Sextractor just asking, give me some kind of ID, give me right extension declination, and give me the center of all the targets you find, and give me some magnitude. That's all I need for now. Once I have this Sextractor output, I'm going to put it into IRF, so to translate it into this format that GMMPs likes. So the task to do that is called this STSDAS to object. And then you give this is the fit table that you generated. Well, this is the place where this task is located in the Gemini IRF package. And then basically you're gonna change a little bit the columns. And this is the output. The output looks almost the same as before. If you remember the other one, for example, the magnitude now is in the 3rd column or 4th column instead of the 5th. So this is the format that SkyCat likes. And the names of the columns change a little as well. And in this case, there is an added column that is called priority, and we're gonna play a little bit with this priority after. So this is a table that looks very similar to our original table that has basically one entry for each of our sources in our field, and this is called the object table. It's a fits table, just like the other one, and this is the format that GMMPs likes. We're gonna feed this into GMMPs, and with GMMPs we're gonna start playing a little bit to give enough material to design a mask. So I'm going to load. This is GMMPs now. I'm going to load my image. Go to File, Open, load my image, the pre-image I showed you before, and then I'm going to load my object table. And my object table has many things. Basically, this is I shoot a cannon. I'm just like, okay, doesn't matter. Give me everything. So in this case, Sextractor gave me 4,000, almost 5,000 sources. And that's fine. We can start with that. We can be more careful. We can remove things before if we want, or we can start with this. It doesn't matter. This is just like Rodrigo showed you before. This is the section where we're going to design the mask. We can only use targets inside this this area, and this area comes from what I told you at the beginning. You decide when you take your pre-image, you decide what is the center of your field, what is the position angle, and then you're stuck with that. And so that's when you need to be careful deciding both things, because then you kind of really rotate things after, because then you need a new guy starting. It's a mess. You need to be very clear from the beginning. when you're using pre-images. So something that Rodrigo told you already also is that you need these alignment stars. So what are these guys? These are stars inside your mask that the observer is going to use to align the mask. You're putting something in your optical path, and then you need to make a little adjustment so your mask is in a perfect position. So so all the slits fall inside. All the slits fall on top of your targets. So usually 3 is what you want to go. You want them well distributed, so you can have a very, very good alignment. You don't want them very close, that's kind of useless. And you want them with similar magnitude within 1 meg. And you want them to be observable, to be visible in some kind of short exposure. Remember that in the near infrared, we cannot do very long exposures. So in a short exposure, you should be able to see these stars. So this is what I did here. This is, again, my object table. I look for them in my image, and I chose these 3 stars, and I can, just like Rodrigo showed you, you can operate this table directly. In this case, if I click in this acquisition, these 3 targets that were just a simple another target, just like any other, I'm going to make them acquisition star just by clicking on this acquisition box there. And this is the result. What changed is that the priority now is set to 0. I'm telling these guys are acquisition stars, and these are boxes, those little boxes, 2 by 2 seconds. And where are my acquisition stars? Is one here, and one here, around here, I think. I cannot see it. There. So this is my whole mask, and I have my stars well positioned in different places, so I can have a proper alignment. And 3 stars, and within 1 magnitude, so I follow my own instructions, and it looks very nice. Now, what we had at the beginning was that we gave this priority of 3 to everything, just flat priority to everything, and then we have this gazillion of targets. But there are some targets that I really want them inside my mask, so I'm going to give them a higher priority. And I can do that again directly here, operating this observing a table, just by clicking on things and then changing here. I click priority 1, and things are going to change. I'm going to have a higher priority to be included inside my final mask. Okay, and now this is the important part. What is different from the optical? What is different is, I told you, so we need to somehow subtract the sky, understand the sky is subtracted. So there are 2 ways to do this. You can do the standard thing that you do in the near infrared, that is this nodding. So you're going to move the telescope in the same direction of the slits. So if you have a slit, let's say 5 seconds like this, and your star is here, then you're going to move the telescope. And when you move the telescope, you move everything. You move all the slits, and then all your targets are going to be in this, what we call the A position. You're going to take a spectrum, and then you're going to move in the different direction. You're going to move the telescope in the opposite direction, and then your target is going to be in this B position. Then you're going to take a spectrum here. And this is the game you're going to be doing. You're going to be taking A, B, A, B, B, A. And that's the classic way to obtain a spectrum in the near infrared. So these are kind of long slits, we call it 5 seconds. You're going to see why I'm calling them long. The advantage is you're always exposing, always taking data. These are kind of long, so you don't have this huge number of slits. And this is going to work well as long as the objects are kind of isolated. If you have more stuff here, like in my case, I have this field in the bulge, many stuff. So there's always something else. So probably for a field that is as crowded as something in the bulge, you don't want to do this. You want to do something like this. What you do, this is the second option, is that you do a very short slit, and you put your star, and then to obtain the sky, you go somewhere else. You move your telescope into a blank field, and this is going to be your sky. And then you come back, and then you go somewhere else, and then you go somewhere else and come back. So the advantage here is, well, you can put more slits because these are very short. But the disadvantage is that you're spending half your time on the sky. But this is probably if you have something very crowded, or you are observing something, I don't know, some kind of star-forming region inside a spiral galaxy, then maybe this is the only way to do it, because you don't have a sky within your slit. You need to go somewhere else to obtain your sky, so you can subtract the sky. I'm running out of time. I'm going to tell you something about the slit widths that I mentioned before. in gmmps, you can design whatever slit width you want, but you should stick to these sizes, because at some point you need to do telluric correction. Telluric correction means you're gonna need to start a telluric standard so you can remove this contribution of the Earth's atmosphere. So that's why you need to stick to these slit widths, because these are the slit widths of the long slits. Of the long slits that are going to give you the observations for the telluric standards. Finally, you design you put your acquisition star, you put your priority. Finally, you can click, okay, I'm ready, configure my mask. And you're going to make sure this is the thing you're going to obtain after that. And this, just like Rodrigo told you, these have to be consistent with what you put in the observing tool, you know, the prism, your filter. This is something very important. This is separation between the slits. You cannot put them very close, because then you're going to have issues. You're going to have issues reducing your data. So you stick with something like 4 pixels distance between the slits. Don't get too greedy, because otherwise you're going to have pain when you reduce the data. And then finally, okay, I'm ready. Boom, make my mask. And my mask, again, this is the same thing Rodrigo told before. Make sure that these things that are here are the same that are in the observing tool, because these two tasks by themselves are not talking to each other. You have to make them talk. You have to make sure that they are consistent. And finally, you have your mask. This is the final step. I have a mask with my alignment stars here, my 3 alignment stars, and lots of slits and everything. All my, supposedly the members of this mystery star cluster, I'm observing some of them. And just here, this is my final slide, actually, just making a zoom. You can see the targets inside the slit very nicely. My guide star, my alignment stars very nicely inside their boxes. And my mask is ready to be cut and to go to the telescope and to be observed. That's all I had. If you want to read more, please read more. This is documentation already. Rodrigo told you about this one. This is the official documentation. If you want to learn more about, in general, the near-infrared sky and the things we need to do to understand the near-infrared sky and to remove it from our data, go to this one. I like it very much. Just like Rodrigo, I have sessions for questions tomorrow and Wednesday. So if you want to know more about the instrument or MOS or reduction, I don't know, just let me know. That's it. Thank you.
Thanks so much, Ricardo. So we have one question already. Given that Gemini is moving its data reduction tools away from IREF, will the same happen with its mask making tools like GMSK create, the IREF-based command?
I think so. Eventually.
Okay.
I think eventually, yes. The thing these are not. There's a whole redevelopment of what is called the OCS, the Observatory Control System, and gmmps eventually is going to be part of that, but it's not yet in the plan. So it's gonna change, but not yet. I think in a few years from now, the plan is to
I think that this is Rodrigo. I think that that is a good question also for Kathleen Labrie. In the future, in the talk about the future of the Gemini data reduction, because it's part of the GMOS, the data reduction is MOS tool, right? Then something that maybe we can, but eventually we have to migrate to other suite like other than IREF and PIREF.
Right. I don't see any other additional questions. And as Rodrigo and Ricardo, oh, there's a new one. Okay. In the past, this question was posted by Bruno Diaz. In the past, the masks were cut in Gemini South for Gemini South projects. This semester 21B, the masks for Gemini South are cut in Gemini North, and therefore I am worried with the shipping complications during pandemics. Why the masks are not cut in Gemini South anymore? How is it going with the masks traveling from Hawaii to Chile? Good or bad experience?
Well, I mean, I can answer that question.
Yeah.
We're
ahead.
cutting a mask at Gemini North since 2020 semester. The problem is that the mask cutter machine here in the south suffered a technical failure. Then to replace this one of the devices there in the laser cutting machine requires some spares from a company in United States, and given the pandemic, we couldn't get it. And then also they have to fabricate. This is something that we will have to leave until the Gemini South laser cutting machine is repaired. And normally, right now, it's taking between 2-3 weeks. I will say 3 weeks between the mask is accepted by Gemini and submitted to the north, and they cut, and the mask is here in Chile. It's about, you have to count about 3 weeks. This is very important. This is why using pre-images could take more time, I mean, than if you use your own external image or external catalog to make your mask.
Okay, thanks, Rodrigo. We have one more question from Joel. So are there F2 spectral resolutions quoted for a 0.5 arcsecond slit that you use?
Yes.
This is Ricardo. Yeah, go ahead.
Where is this? This one. Yes, I believe they are. Yeah.
Yeah. Right. Okay. And let me refresh one more time. It's getting very late here, but okay, I think, yeah, that was all from the audience. And I'd like to thank Rodrigo and Ricardo to prepare this nice workshop. And also to wrap up, this is our wrapping up of the first day. I'd like to thank everyone staying till this late, especially like muchas gracias to todos en Chile and Argentina, especialmente, and muito obrigada Brazil, the people in Brazil. I don't speak Portuguese much. And yeah. 아침 일찍 일어나신 한국 분들 감사합니다. So tomorrow we are starting at 6 p.m. in Chile time. So that's noon in Hawaii and 7 p.m. in Argentina and Brazil and 7 a.m. in Korea. So, except if you sign up for chat session starts a little bit earlier, but the regular presentation starts at 6 p.m. in Chile. Let me check. That's all I had to say. And thanks everyone. Good night. Buenas noches and good morning, good afternoon. Yeah, have a great day, great night. All right. Bye. See you all tomorrow.